Good afternoon and welcome to our afternoon lesson. We are still on heating effect of a current carrying conductor, and in our previous lesson we were able to discover that actually an electric current carrying conductor can produce heating effect depending on the resistance that is offered by the same to the flow of electric charges. We also looked at a few factors that affect this effect of the conductor to produce the heating effect, and they were about 3. We looked at time, resistance, and current. Whereby we said that for us to study any one of them, we have to hold the other 2 constant. Now, from the 3, we came up with an equation which relates the 3 of them, and which we called the Joule's law of electrical heating, and that is where we want to build our lesson upon this afternoon. Probably find out how each one of them affects this effect of a current carrying conductor to produce the heating effect. Now, we start by looking at energy, which we are also going to refer to as heat, or we can also call it the work done. The work done. And this is what we looked at as being equal to current squared multiplied by resistance and time. But we recall that I is equal to V over R, where I is our current, V is the voltage, and R is the resistance. Now, we can substitute. Let us call the first equation star. We want to substitute that expression in our equation star. So we write substituting for I in star. Now, therefore, that means that in place of I, we can put V over R, so that now our heat, or the work, or the energy is going to be V squared over R squared, then R T. Now, we can be able to cancel the like terms, so that now one of the R's go, and we have V squared T over R as our new expression, V squared T over R. Therefore, work done, all the energy converted to heat can be given by V squared T over R, which can be also taken to be equal to I squared R T. Remember that whenever it is that we are looking at equations, it is good for you to be able to point out what each of your symbols stands for. so that whoever it is that is looking at your work will understand what you mean by your symbols. So in our case here, V is our voltage, T is the time factor, R is the resistance, I is the current. Therefore, work done, which we are also going to call energy, in this case it's the heat energy, can be given by any of those two. Now, depending on the information provided by the question, that informs your choice of formula when you are working out any of these factors that are involved in our equation. Now, let us look at an example. Now, our question reads, the potential difference across a lamp is 12 volts. Determine the electrical energy changed to heat and light when a charge of 5 coulombs passes through it. When a charge of 5 coulombs passes through it. Now, let us look at the solution to that. We've been given the potential difference or the voltage as 12. Then we have charge as 5. Now, we want to find out the amount of heat that is produced in this case. But we said that heat could be taken to mean the work done. And in our case here, work is given by charge multiplied by the potential difference. And therefore, we can substitute in our equation so that now work becomes our charge, which is 5 coulombs, and we multiply by our potential difference, which is 12 volts, and the amount of heat is 60 joules. 60 joules. Remember that heat is a form of energy, and therefore it's proper to express it using the units of energy. Now, part B of the question, part B, requires us to get the amount of heat produced when a current of 2 amperes flows through the lamp for 10 seconds. Now, again, we start by looking at the information we have been given. We have voltage as 12, time is 10 seconds, and current is 2 amperes. So we pick on an expression of work which relates the three, and we have one where work is given by the product of voltage, time, and current, and ours is to substitute for all of them So that now we have 12 volts multiplied by 10 seconds and a current of 2 amperes, giving us an energy 240 joules. 240 joules. Now we look at yet another question. Yet another one. The question reads that an iron box has a resistance coil of 30 ohms and takes a current of 10 amperes. So we are required to calculate the heat developed in 1 minute, and the units should be kilojoules. Again, you ask yourself, what does the question provide? In our case here, we have the resistance, which is 30 ohms. 30 ohms. We have current, which is 10 amperes. And we have time, which is 1 minute. And we convert that one to seconds, so that now we have 60 seconds. Now, in the case where you are working on questions that relate more than one quantity, it is proper to express each one of them in SI units so that your accuracy is assured. So now, looking at what we have and bearing in mind that we are after the heat produced, you ask yourself, is there an equation that relates the three? You have resistance, you have current, and you have time. So you will look for an expression that takes care of the three. And we had one where heat is given by the square of current multiplied by resistance and the time. And therefore, we substitute in the equation. We can substitute for the same in the equation, so that now our heat, all the work done, all the energy will be given by current squared. We multiply this by our resistance and time, so that now we have we have 180 joules. But remember, the question required us to express our answer in kilojoules, so we can convert what we have into kilojoules, and this one will be achieved by dividing by 1,000 throughout, so that we have now 180 kilojoules as our final answer. Let us look at a final example. Look at a final example. Now, the question reads, a heating coil providing 3,600 joules per minute is required when the potential difference across it is 24 volts. Now, the question requires us to come up with the length of the wire that makes the coil, given that its cross-section area is 1 times 10 to the power -7 meters, and the resistivity has also been given as that. Now again, Let us look at the information we have. We have power as 3,600 joules per minute. Now, we have voltage as 24 volts. We have cross-section area, and we have resistivity as 1 times 10 to the power 6 ohms meters. Now, let us use the information to work out the length of our wire. But power is given by 3,600, that is per second. So that now the power per second is going to be 60 watts. That is, remember that we had been given power as joules per minutes. We would like now to work with SI units. Therefore, we should look for the power that is supplied in 1 second, and that is achieved by dividing by 60. But power is given by V squared over R, which means that now the resistance is going to be given by V squared over power. The resistance of the wire is going to be given by V squared over R, and V has been given as 24. We square that and we divide by our power in SI units, which will give us 576 divided by 60, and we have a resistance of 9.6 ohms. Now, with the resistance, then we can use the equation of resistivity, where we have resistance being equal to resistivity multiplied by 1 over cross-section area, and not 1 but L for length. That resistance is resistivity multiplied by L over area, and we can again substitute, so that 9.6 will be given by resistivity, which was given as 1 times 10 to the power 6 ohms meters. Then the length, which we are looking for, then we divide by the area, which again had been given as 1 times 10 to the power negative 7 meters squared. And once we work that one out, we are going to be left by with length being equal to 9.6 times 1 times 10 to the power 7 meters squared. This one should be divided by 1 times 10 to the power 6, and that one gives you a length of 0.96 meters. 0.96 meters. Therefore, you remember that you will always have to work with SI unit. We started by changing our power, which was given in joules per minutes. We converted it to joules per second. We achieved that by dividing by 60. Then we went on to look for another expression, which gave us power as V squared divided by R, and that one enabled us to come up with resistance. And now we have roped in the equation that relates length, resistivity, cross-section area, and resistance for us to be able to come up with an expression of length. Now, let us now look at power and energy. We have already calculated the energy that is converted by this current carrying conductor into heat. Now we want to look at power. So electrical energy and power. You recall that we have had two expressions, heat, or what we are calling the energy, as I squared RT. We have also gotten another one as V squared T over R. Now we want to move from these two and come up with expressions of power. Now, for number one, we note that work in itself is given by charge. You multiply by voltage. This is where I want us to begin. That work is given by charge over voltage, but charge is given by IT. You can call that one star 1. Therefore, we want to substitute this in 1. So substituting for Q in 1, you find that now work is given by ITV. You can call that one equation 2. But we are not interested in work. We want an expression of power. Therefore, we say, but power is given by work over time, implying that now equation 2 is going to be VIT over T. You can cancel, and therefore power is given by voltage times current. That one is equation A. That one is the first equation of power. But you could also bring in the Ohm's law, and you say, but from Ohm's law, V is equal to IR. Now from Ohm's law, voltage is a product of current and resistance. Now therefore, substitute for V in A. Substitute for V in A, so that now P becomes, in place of V, you put IR, so that now we have IR dot I, and therefore P is I squared R. Call that one equation B. But I is equal to V over R. Now, in place of I, we want to substitute. In place of I in equation B, we can substitute by V, by putting in V over R in place of I. So, substituting for I in B. Now, we want to put in the value of I in our equation B. So in place of I, we put V squared, V over R. We square this, and then multiplied by R is going to give us our P. So P will be V squared over R squared multiplied by R, which gives us V squared over R. You can call that one equation C. So basically we can have those three equations. We have equation A, B, and C, all of them derived from the expression of work. You start by looking at work as charge times voltage, but again you have an equation that relates current and time, that the product of which gives us a charge. You substitute for Q in your first equation, so that now work is given by the product of voltage, time, and current. But now we know that work divided by time is what gives us power. So you can divide the equation of work so that we can get the first expression of power. Now again, you note that from Ohm's law, voltage is given by resistance multiplied by current. Therefore, from your first expression, you can substitute for V, and in the place of V, we can put now this newly found expression IR, so that now we can have the second expression of power as the product of current squared and resistance. Now the final one will be given by substituting for I from the Ohm's law. You can be able to make I the subject of the formula, and from that you can come up with this a value of I as a factor of voltage and resistance, and you can put it in your equation B, so that you can come up with the third expression. So basically we have those three equations of power. Let me write them down here. Equation 1, power is given by VI. Equation 2, power is the product of I squared R. And equation 3, power is given by V squared over R. Now we are going to use those equations in our next examples. Now, the question reads, determine the electrical energy in joules that a 150 watts lamp converts to heat in part A, 5 seconds, and part B is 1 minute. Now, the question is on energy. Energy. We have been given the power, we have been given the time, but power is given by work divided by time. Therefore, if you want the work, making it the subject of the formula, work times time, power times time. Work is given by power times time. So part A, power is 150 watts and time is 5 seconds. So the amount of energy will be given by the product of that, which gives you 750 joules. Now part B, we have the same power, 150 watts, but now the time is given in minutes. Therefore, we have to convert that to seconds by multiplying the time by 60. And the product of that is about 9,000 joules. 9,000 joules. We look at another example. Calculate the current that a bulb rated 100 watts and designed for a mains supply of 250 volts draws when operating normally. When operating normally. Now, from the information that we have been given, voltage is 250 volts, power is 100 watts, and we want to get the current. The question requires us to get the current. Now, but from the expression of power, we know that power is equal to voltage times current. Voltage times current. Therefore, let us substitute so that now 100 is equal to 250 multiplied by current. Multiplied by current. And therefore, current as a subject of the formula will be given by 100 divided by 250, and these ones will be amperes, and we have a current of 0.4 amperes. 0.4 amperes. What is the operating resistance of an electrical lamp rated 60 watts, 240 volts? Here we have voltage as 240, power 60 watts, and we want the resistance. So we go back to our three expressions, find out whether we have one relating the three. The expressions of power, find out whether there is one that relates the three. And power is given by voltage squared divided by resistance. Therefore, let us substitute so that we can find the resistance, the operating resistance of the lamp. And the power is 60 watts, which is given by 240 squared divided by resistance. Over R. Let us make the resistance the subject of the formula, since it's the quantity we want to calculate, so that now R will be given by 240 squared, and this one we divide by 60, so that now resistance is 960 ohms. 960 ohms. 960 ohms. Now, I want to give an assignment. About 2 questions you should try and solve in the course of your revision. Question 1. A house has 2 20 60 watts bulbs, 2 1000 watts heaters, and 2 500 watts security lights. Now, all of them are supposed to be switched on concurrently, and they are running on 240 volts. Now, I want you to find out how much power in kilowatts is going to be used when all of them have been switched on, and the total current that is drawn from the supply. One last question. What is the operating resistance of a lamp rated 600 watts, 300 volts? 60 watts, 300 volts. Now that's about all for today. When next we meet, we talk about applications. Thank you.